In this chapter, we will be studying the derivative rules. In this lesson, we will be looking at higher derivatives.
Okay, everyone. Today we're going to talk about higher derivatives because it's an interesting thing about a derivative, okay, that when you take the derivative of a function, every function, you get another function, okay? So the derivative will always be a function when you take the derivative of a function. So that makes sense. And that means that we can take the derivative of it too. And the result is the second derivative. So instead of having that single apostrophe there, we have two apostrophes. We call that the second derivative. I know not a lot of creativity went into naming that, but that's what we call it. Now, there are a few different ways of representing these things, and there's a couple of these that I really want to draw your attention to. First of all, most of the time we're going to use, in this particular course, the double primed. Okay, so y double primed or f double primed. But we're also going to use this particular notation quite a bit. So d squared of y over dx squared. Now, it's very interesting where the squares are going here. Notice that that square doesn't go outside here, okay? If it did, if you had dy within brackets with a square outside and the dx with a square outside down here, that would mean that you're squaring the derivative, okay? But here, when we put the square on the d like this and the square outside this, what we're doing here is we're saying that we're taking the derivative twice of y, okay? And that's an important little bit of notation here. It's a very subtle little bit, and I think a lot of times people will glance over that and not really think about what's being said here, but that is important, that square is on the d, not on the dy. Anyway, we'll see that come up a little bit later on in the course here as well. Another way of doing this is d squared of f of x, or d squared, and we use the x down there just to tell us what the independent variable is of f. Okay, so what we're going to do here is we're going to find the second derivative of y equals negative 7x to the fourth plus 5x cubed. That little bit there should have been down one more line here. But just to illustrate how you do this, because this is not a big deal. So the first derivative, we're going to bring down the exponent. So 4 times negative 7, negative 28x cubed. Then bring down the 3, so 15x squared. So there's our first derivative, and then we just do it again. So the second derivative, okay, we bring the 3 down. Okay, 3 times negative 28 will be negative 84x squared. Bring the 2 down, 30x. And that's all it is. Okay, there's really nothing more complicated than that. He said, knowing that sometimes it gets a little bit more complicated than that, but we'll get to that in just a little bit here. Now, just some stuff about the first derivative. Okay, we know that that is the slope of the tangent line to the curve. So when you take the second derivative, what this is it's the tangent line to the tangent line. And so what that does, okay, that tells you how the slope of the tangent line to the graph of f of x changes as x changes. Now, so let's think about that. The first derivative is the slope of the tangent line to the graph. We know that that is a rate of change. It's an instantaneous rate of change. So now let's just think that through. So if you take the derivative of the derivative, that second derivative is going to be the rate of change of the slope of the tangent to the function. And so that is related to the type of curvature we're seeing in the graph. Now, just give you a little bit of indication. So what we mean by that is whether you got a curve that curves like this or curves like this. Is it a gentle curve? Is it an extreme curve? Does it happen quickly? Is the curve up? Is it down? That's what that second derivative is going to tell us. And again, that is something that we will explore a little bit later in this course. The third derivative, okay? So we put 3 little apostrophes there, f triple primed. And again, notice the notation here, that 3 is on the d. It's not on the whole thing, because again, I'm not cubing the derivative. I'm doing the derivative 3 times of the function y. Okay, so I'm applying this derivative function 3 times to the function y. And again, another way of writing that is d cubed. Now, you might think, well, the fourth derivative, surely that's going to be primed. Okay, the fifth derivative would be prime. Okay, well, no, we don't do that. Okay, anytime you go beyond the third derivative, what we do is we're going to put in parentheses up in the exponent the derivative, the number of derivatives that we're taking here. So fourth derivative, fifth derivative, sixth derivative, and so on. Okay, so anytime you see that, anytime you see an exponent written like this, I mean, if I wanted y to the fourth, I wouldn't put parentheses there. So that when I see the parentheses like that, when I see that bit of notation there, I know that it's a derivative. I know that it's a fourth derivative. Okay. Now, like I said, all we're doing is taking the derivative of a derivative. Okay. In most cases, it's just as straightforward as that. However, there are a couple of things that I need you to be looking for and to be prepared for when they show up here. So we're going to run through a handful of examples here, and I'll highlight the little twists that these kind of questions can take as we get through them. Okay, so for our first example, we're going to say that y is equal to x squared over x minus 2, and we're going to find the second derivative. Okay, well, to do that, let's find the first derivative. So y primed, okay, is going to equal, and now what we're going to do here is we're going to use the quotient rule. So it'll be the derivative of the numerator, okay, multiplied by the denominator, minus the derivative of the denominator, which in this case is just going to be 1, times the numerator, x squared, all over the denominator squared. Okay, now, the best thing to do here before I move on to the second derivative is to simplify the numerator here. So I'm going to distribute the 2x through. So 2x squared minus 4x minus x squared all over x minus 2 squared. Okay, and there's just a little bit of simplification I can do here. 2x squared minus x squared will get me x squared minus 4x all over x minus 2 squared. All right, now I can take the second derivative because I've got the first derivative here. Now, don't feel obliged to like try to simplify that down a little bit further by like factoring out the x or whatever from the numerator. Nothing's really going to cancel there, so that's about the best we can do. So let's try now taking the second derivative. Okay. Now, comparing the original function to the first derivative, when you're taking a look at that, think, well, it got a little bit more complicated. Maybe that's kind of the general rule here, that when you take a derivative, the expression, especially if it's a rational, is going to get more and more complicated. Well, let's take a look. The derivative of the numerator will be 2x minus 4. Okay, and we will multiply that by x minus 2 squared, the denominator. And then, well, sorry, that doesn't really look like a 4 over there. There we go. Minus the derivative of the denominator, which will be 2, x minus 2. This just requires the chain rule. And then the derivative of what's inside there would just be 1, multiplied by the numerator, x squared minus 4x. And that is all over. In this case, this will be x minus 2 to the fourth because we square the denominator. Okay, well, that has gotten a little bit uglier. Okay, but let's see what we can do with it. Well, first of all, I can factor out a 2 out of here, and there is a 2 right there. I can also factor out 1x minus 2 out of both of those terms there. So I will get a 2x minus 2. That is going to leave me with, in this first expression, I'm going to get an x minus 2. When I take out that 2 from that first factor there, I'm going to get an x minus 2 left over. And I've still got an x minus 2 left over there. So that's still going to give me x, whoops, that's right. Let me just clean that up a little bit there. I'm still going to get an x minus 2 squared here, minus x squared minus 4x. Okay, so close the brackets, and then for the numerator, and then this is all over x minus 2 to the fourth. Okay, well, I already see that there's an x minus 2 that's going to cancel with that, so there's going to be a cube down there. Now what I got to do is I got to expand out and simplify what's happening inside the brackets in the numerator. So I've still got that 2 there. This first binomial squared here will become x squared minus 4x plus 4. Okay. And then that negative will distribute through minus x squared. Well, actually, I kind of like that. That minus x squared is going to cancel. Positive 4x. Oh, I like that too, because that's going to cancel with that negative 4x that's up front there. And I've still got x minus 2 cubed in the denominator. Putting those together, the x squareds cancel, the negative 4x, here, I'll do that. The x squareds cancel. The negative 4x and the positive 4x, they balance each other out there. And so what I'm left with in the numerator here is this 2 times the 4, or 8, over x minus 2 cubed. Okay? And notice in this case here that, yeah, although the first derivative did become a more complicated expression, actually the second derivative became a lot more manageable. Okay. Now, granted, we got this cubic in the denominator, but the numerator became a lot friendlier. And in fact, if I was to continue to take the derivatives here, it will be a nicer expression. Let's take a look at some other examples. All right. So in this question, we read that y is equal to y is equal to 5x cubed minus 4x squared plus 7x minus 3. We're going to find all of the higher derivatives. This one is a little bit different than the one that we just did because this is a polynomial, not a rational expression here. So things behave a little bit differently here. Things will naturally simplify as we go along here. So let's just take a quick look here. My first derivative, take the derivative of each term individually. So that will become 15x squared minus 8x plus 7. Now, notice the derivative of the negative 3 is 0. And like we said before in a previous lesson, when you take the derivative, the degree of the function drops by 1. So our cubic became a quadratic. Now let's take the derivative again. Okay, 15x squared will become 30x minus 8. And again, that constant there, that 7, okay, which in the original used to be a linear term, became a constant, now disappears. Okay. Now let's take the derivative one more time. Now I expect my linear to become a constant. So the third derivative, okay, when I take the third derivative, that's just going to be 30. So I take it down to a constant. So 3 derivatives down from a cubic, I get a constant. And now, and remember the notation here, I'm going to put a 4 up in the parentheses there, up in the exponent. When I take the derivative of 30, I get 0. And from this point on, they will all be 0, okay? So at this point here, as long as n is greater than or equal to 4, the nth derivative of this polynomial function will be 0. That's all of them. All right, in this question, we are given that 2y minus y squared equals 4x, and we're asked to evaluate the second derivative at the point negative 2, 4. Now, notice that the way the function is given to us, you can probably tell right away, is going to require implicit differentiation to find the second derivative of this. Okay, and actually, this is why we wanted to go through this. I want you to see an example of this. So here we go. So to take the derivative of 2y, okay, we're going to take the derivative of the outer term, which is simply going to be 2. Okay, but then remember that y represents a function of x that we can't see. So I'm going to have to multiply by the derivative of that internal function, which would be y prime. I don't know what it is, but I know that a derivative belongs there. Minus the derivative of y squared will be 2y. And now I need to multiply by the derivative of the interior function, just like I did before, but I don't know what it is, so I put a y prime there. Okay, and on the right-hand side, this is simply going to be equal to 4. Now, the nice thing about the way derivatives work is they are linear in the sense that I will be able to easily solve for y primed. Okay, I am going to, in fact, actually, I'll do this a slightly different way. I was going to jump into that a little bit quicker than I should have. What I'm going to do here is I'm going to factor out the y primed on the left-hand side here, I should say, to get 2 minus 2y is equal to 4. Okay, and now I'm going to divide by that 2 minus 2y to get y primed is equal to 4 over 2 minus 2y. And now I've been able to get the y prime by itself here, and I should always be able to do that. Now, to simplify that one step further, I notice that every term there is divisible by 2, so I will do that. And that'll get me 2 over 1 minus y. Now, I know that I'm going to take the derivative again here in just a moment, So what I'm going to do is I'm going to find y prime. I'm going to bring that 1 minus y up. Make this 1 minus y to the negative 1. That's just going to make it a little bit easier for me when I find the second derivative, which is what I'm about to do right now. So I've got y primed. I've got it in a form that I'm comfortable taking the derivative with. So here we go. When you take the derivative of y primed, you're going to get y double primed. Okay? So on the left-hand side, that y prime becomes y double primed. Now, on the right-hand side, notice there's no x anymore. The independent variable is disappeared. This is in terms of the dependent variable only. So again, I'm going to have to take the derivative implicitly. So, but I can see the chain rule there. So I'm going to take the derivative of what's outside. Okay, so that'll be bringing down the negative 1 to get negative 2, 1 minus y to the negative 2. Okay, now I got to multiply by the derivative of what's inside, and the derivative of what's inside, 1 minus y, will be negative 1. And now I have to multiply by the derivative of what's even deeper than that, whatever's inside that function y. I don't know what that is, so I'm going to use y primed to represent that. Now, this might be confusing because you might look at this and think, well, aren't we taking the second derivative? Yes, we are. But when you take the derivative down here of y primed, that's where you get the second derivative. But remember, all I'm doing to this function down here is taking a derivative. It just so happens that ends up being the second derivative of this term right here. But when I get down to here, since it's y all by itself, when I take that derivative, that is the first derivative of y right there that pops out. And so now, when I simplify this, I've got the negative 1 times the negative 2. That's going to be 2 over, and I'm going to move that 1 minus y down to the denominator, 1 minus y squared. But notice I've got this y primed hanging out at the end here. But, and this is what I want you to notice here, I can go a little bit further here, and in fact, it's one of these rules here. I don't want to write a derivative in terms of another derivative. So I don't actually want to have this y primed left over there. But that's okay. I know what y primed is equal to, so I can make a substitution. So I've got 2 over 1 minus y squared. Okay. Oh, it's coming in slow here. And then that y primed can be replaced with 2 over 1 minus y. And now I can put these two factors together, and I will get that the second derivative, and I probably should have written that all the way down there, but the second derivative here is going to be equal to 4 over 1 minus y cubed. Oh, there we go. 4 over 1 minus y cubed. There we go. And that's the second derivative that we're looking for. Now, to evaluate that at the point negative 2, 4, well, I'm going to plug in the values of my variables here. So I've got this second derivative. I'm going to evaluate that at the point negative 2, 4. But the interesting thing about this is that the second derivative doesn't depend on the x-coordinate explicitly, only implicitly. Okay, whoops. It's not quite clear here. In other words, there's no x that appears in this second derivative. All that appears there is the y. So all I'm going to do is enter in that y, 1 minus 4 cubed. And I would like to have done this vertically and move this down, but obviously you can see I'm running out of room here. So in the denominator, 1 minus 4 will be negative 3. Cubed will be negative 27. So I just move that negative out front, and my final answer becomes negative 4 over 27. That's the value of the second derivative at negative 2, 4. Okay, one more example here. Let's find the second derivative of x squared plus y squared equals 4. Okay, so to start off with, I can see again that I'm going to probably do this implicitly. I could solve for y. I could, but I'm going to end up with a radical function in there, and basically two radical functions, the positive and the negative one here. It's probably just easier to do this implicitly. So let's take the derivative here of x squared will be 2x. Okay, not a problem with that. Plus 2y but again, because the y represents a function of x, I would have to multiply by its derivative inside here. So I'm just going to write y prime to represent that derivative. And that is going to equal 0. Now, very common mistake to all of a sudden put a 4 in there to forget that first rule, okay? That the constant rule, that the derivative of a constant is 0. Anyway, so here we go. Now what I'm going to do here is I'm going to isolate the y prime. So I'm going to move the 2x over, divide by 2y. So, well, I'll do that in steps here. So 2y primed, sorry, 2y primed is going to equal to negative 2x. And then I'm going to divide by that 2y, and I will get that y, sorry, I don't know why I have double prime there. I will get that y primed is going to equal simply negative x over y. Okay. Here it comes. There it goes. Okay, good. Now, to get my second derivative, I just take the derivative of this function. Now, remember, what I'm doing here is I am taking a derivative. I'm basically doing it again. So I'm taking the derivative of all of these terms here again. So the derivative of y primed, because it's already had a derivative taken, the derivative of y primed is, in fact, my y double primed. Okay? Now, the negative x over y, I'm going to apply the quotient rule to this. So the derivative of x is going to be 1. So it'll be just negative 1 multiplied by y. Okay? The derivative of y, sorry, this will be minus the derivative of y, which is just y primed. I don't know what function that is, so I'm just going to use the y primed to represent its derivative, and that would be multiplied by negative x all over, okay, just waiting for this to come in here, all over y squared. Okay, now I'm going to simplify that just a little bit here. There's really not much I can do. Right now, there's something I got to say here, but I'll get to that in just a second. So this becomes negative y plus xy primed over y squared. Basically, I'm just canceling the negatives in that second term in the numerator. Okay? All right. Now, but remember what I said in the previous example here. We don't like to write derivatives in terms of other derivatives. In fact, we really shouldn't. Derivatives should be written solely in terms of the independent and dependent variables here. So I don't like having this y primed right in there. I don't want it. That's okay, because I already know what y primed is, and I should know that already. Okay, because when you take a derivative, it shouldn't be too difficult to isolate that derivative. So then I'll have an expression for it that I can plug in later on. So now I'm going to do that substitution. So my second derivative, okay, y double primed here, and I don't know where my y went, y double primed is going to equal, okay, negative y plus x multiplied by negative x over y all over y squared. Just waiting for this computer to catch up here. So there's that negative x over y when it shows up. Oops, you're not seeing the line there. Negative x over y, that was the y primed. So now what I'm seeing here is I've got this negative y minus x squared over y all over y squared. Now something neat is going to happen here in just a second, okay? Well, assuming the computer was able to catch up, and there it is. Now, in the numerator, what I'm going to do here is I'm going to get a common denominator of y. So that negative y over 1 will become negative y squared. This will become minus x squared over y all over y squared. Okay, so all I did was multiply that first term, numerator, denominator, by y over y. Okay, so that's where I'm getting that negative y squared, and then because the denominators are the same, minus x squared over y squared. Okay, now what's interesting here is that negative y squared minus y squared sorry, minus x squared. I can't believe I said that. But what I want to point out here is that over y squared is going to become over y cubed. Okay. So, and if you're not sure about what's going on there, bear in mind that I'm dividing by y squared, which is going to be the same as multiplying by 1 over y squared. Okay. Now, that's something I'm hoping you're familiar with there. But again, if you're not, just think that through there. Just divided by y squared is like multiplying by 1 over y squared. Now, I'm running out of a little bit of room here, so I'm just going to come over here. So I'm going to rewrite that. Y double primed is going to equal negative, and I'm just going to factor the negative out of the numerator. Okay, I need to be able to see that there. So y squared plus x squared all over y cubed. Now, I want you to see something here, and just as soon as that pops up here, something that is probably going to show up more than just this once in this particular course here. Okay, because oftentimes I'll have students that'll come to this point and they'll say, well, I don't know what to do with this beyond this point, even though when you look it up in the answer key in the back of like the textbook or whatever, it's substantially simpler. And the reason it's substantially simpler is because of a substitution that gets made. Notice I've got y squared plus x squared sitting right here. Well, where have I seen that before in this problem? Up in the original question. X squared plus y squared is 4. So I can actually use that because remember, that is true in the context of this question. So even at this point, when I'm taking the second derivative here, it is true that x squared plus y squared is still equal to 4. So I can actually substitute that in and make this negative 4 over y cubed. Okay, and it'll look awesome once that pops up. Negative 4 over y cubed. And that is the simplest form of the second derivative that we can get there. But isn't that a neat little thing to happen there, that the original expression pops out in that second derivative, and then we can simply make that substitution to reduce that down even further.
Is negative 4.